Hi, everyone, and thank you for watching this workshop. My name is Francesca Morfini. I am a PhD student at Northeastern University in Boston, and this presentation is part of the 2023 OHBM Educational Day about making quality control part of your analysis. And my talk today is going to focus on functional connectivity, quality control procedures, as can be performed with the CONN toolbox. I have no disclosures to report. And today I will give a walkthrough of quality control procedures using data from the FMRI Open QC Project. And specifically, I'll be using resting state data as one could do if interested in performing functional connectivity analysis. And I hope that today's presentation will speak to two general concepts. The first being that while it is easier to agree upon a final goal for quality control, this being to ensure good data quality, it is a little bit more challenging to agree upon on how to achieve such outcome. And while I will be showcasing one approach, there are many others which would be equally useful and just as effective. And secondly, I want to emphasize how both qualitative and quantitative quality control procedures are useful tools to use. They're not just complementary, but bring to the table information that's non-redundant. So using both together is really conducive to get to know your data. So one way that one could follow to first approach a newly accessed data set is to follow a workflow which helps remind that there are several moments during data processing when it is useful to stop and perform quality control. And here I'm just representing three major points with these blue squares, but obviously there could be many more useful to evaluate as well. And the first quality control decision point or checkpoint has to do with the raw data. So even before starting any sort of like analytical transformation of the data. A first relevant question is whether the characteristics of the data set, for example, the participant demographic or data characteristics directly are in line with one's own research objective. And this is particularly relevant, for example, with open access or publicly available data set. And relatedly, this is a good time to start noting whether there is expected or unexpected heterogeneity in the data. This information can be gathered through various sources, one being, for example, the sidecar JSON files, or also by extracting information from the data itself. And this is also a good moment to start familiarizing oneself with the data by visually inspecting structural and functional data, with the goal, generally speaking, to look for issues which cannot be mitigated by preprocessing and denoising. And such issues might warrant, if found, might warrant exclusion of that data even prior to get to preprocessing and denoising. For example, if functional connectivity or a region of interest, whether it's a cerebellum or there's some cutout portion of the brain that one is interested in studying and it's not present in that specific run, for example. So to give you an example of how this could be approached from the CONN toolbox, I have already opened the CONN toolbox from MATLAB and preloaded a CONN project which I had used to analyze the data. In this case, actually, the data has been fully preprocessed and denoised, so some of the information as CONN displays them now might be slightly different from how they would look like if this was really a raw data level type of inspection. But the general ideas applies as well. So we have structural data, in this case, again, fully preprocessed, so skull strip, normalized, realigned. But one thing that it's useful to do, both before and after preprocessing, is to inspect various slices of each of the structural or anatomical data from different planes for all the subjects, looking for things, again, that might give some insight of issues or heterogeneity, broadly speaking. And one could look at different subjects. Similarly, functional data. Again, here is smoothed because preprocessing has already been applied, but this visualization tool shows the first and the last volume, or TR, acquired for this run for the first subject, and again gives the possibilities to scroll through different planes. And at this level, if we were looking at raw data level, for example, for the functional data, we look at the original data. For example, something that we might notice is that, especially across subjects, is that there is heterogeneity in terms of shape of the brain, spatial alignment, and potentially different types of intensities and different kinds of inhomogeneity of the signal. And to some extent, at the raw level data, this may not necessarily warrant for exclusion, especially because this type of heterogeneity is really a participant level type of characteristics that is somewhat expected. And so one could decide that, perhaps trying to preprocess any noise is a good way to move forward. And once this set of steps are finished, one can move on to preprocess and noise the data, and CONN offers several pre-compiled pipelines for slightly different scenarios, which are constituted by different steps, which gets applied from top to bottom, and these are somewhat modular. And so this pipeline itself can be modified by either removing or adding some specific steps to apply to the data, or changing the order in which they get applied. But the general idea is that after the pipeline of choice is applied, one would land on one would have fully preprocessed data, which then would have to be denoised. And one could decide to, for example, do quality control after preprocessing directly, but potentially one could also apply denoising, and in this case, the elements that will be regressed out from the functional connectivity time series, the functional data time series, are listed in this box. In this case, we're following an ACON core type of denoising approach, in which we're regressing out nuisance factors, or the principal components, the 5 top principal components extracted from white matter and CSF, which would result from segmentation of the structural data applied to the functional data. Realignment parameters, and during processing, we had identified scans or volumes which have a high level of motion above a certain threshold that we had specified, and all of these time points are regressed out, and this is specific for each subject. So there might be different number of volumes to be regressed out. So assuming that we've just run preprocessing and denoising, we're back onto the workflow, and the next major quality control checkpoint is to visually inspecting the data after preprocessing. And this helps identify potential issues that were introduced by the analytical pipeline by mistake. So we had applied a series of steps, but it's not always the case that each step really achieved the goal that it was intended to achieve, and so potentially may even corrupt further the quality of the data. And this is also another moment in which we can assess whether the issues that we have noted at the previous quality control checkpoint that were present in the raw level data are still present after preprocessing, even though we would have expected them to be, if anything, mitigated. But perhaps this hasn't happened at a level in which we are satisfied, for example. And additionally, throughout preprocessing and also denoising, there are several quantitative metrics that are automatically extracted from the data before and after some of the steps that we had applied. This is really interesting and good to look at because it gives you a way to assess how and when potentially data quality improved or got worse for some reason. Assessing the distribution of these quality control metrics can be very useful, for example, to identify runs which deviate significantly from the relative distributions of the remainder of the data set or the rest of the data set. So how this looks like in CONN is the following, basically. So again, if we look at the quality control distributions, and I'm looking at the full data set here, for a subset of QC metrics that I had pre-selected, but generally speaking, this could be very flexible to include other ones. I just pick a subsample, and one could see the relative performance of specific runs as they compare to the rest of the distribution of the data. And so, for example, here we're looking at invalid scans, which is representative of the number of scans that have been identified as motion outlier or outlier based on, for example, global signal change. And as we can see, there's high variability. There are a number of runs that exceed the extreme outliers threshold, which is defined by data points that are above the third quartile plus 3 times the interquartile range. And those would be the subjects for which more volumes will be regressed out during denoising. Another correlated or related measure is PVS, which stands for proportion of valid scan, which represents the ratio between non-outlier scans to all original scans. And so while related to invalid scans, this measure is slightly different in that it's basically a normalized measure of how much of the remainder of the data is left, taking into account the overall data length. So this is very useful, for example, in when a data set has data with different length. And in this case, this data set had a high variability of how much data was acquired per subject. Mean motion is the frame-wise, is the mean values of frame-wise displacement calculated based on only the valid scans. So after regressing out, after removing the scans that are considered outliers. And this measure can be considered as very informative, for example, about the state of the data after preprocessing. So this is sort of a measure of potentially remaining motion level in the data. And finally, norm, func, and norm ANAT represent or measure the similarity between the functional and anatomical data after normalization as compared to the reference MNI template brain. So sort of like a spatial match with the template. And so in this case, lower values here indicate a poor performance of normalization. And here we have two examples that are well below the extreme outlier threshold, which is initially to begin with a threshold that is useful to consider, or at minimum to double check with some more thorough qualitative or visual inspection plots or ways to visualize the data. So, for example, subject 88 and 90 are performing significantly lower, and then there are a couple of other ones. 135, if I recall, was right borderline in between extreme outliers and mild outliers, and it's something that even after having gone through a visual inspection of all of run level quality control plots is something that perhaps one would want to reevaluate again. And so in this case, I picked up these three subjects based on the distribution of norm ANAT, which again is representative of a normalization performance. And if I look at subject 135, which was in between mild and extreme outlier, it seems reasonable. To me, it's the ROI of the gray matter, which is this blue outline, match relatively well with the underlying anatomical slice. And so in retrospect, even if the QA norm ANAT had indicated it as a mild outlier, there's nothing that visually sort of like would speak to a strong case for excluding this subject, given our research goal and our sort of like general approach that we're applying to the whole data set. But obviously there could be other specific reasons why that instead it's to be excluded. When we look at subject 88 and 90 instead, we notice that this norm ANAT was really picking up on something that seems to have gone away, and that looks like the anatomical data is somewhat fragmented. And at this point, because it's really still hard to know exactly what's going on here, again, you can see that it's relatively fragmented, but and here specifically, it's the ROI of the gray matter seems to be very spotted here and there, not continuous. It's not really following the gray matter where we would expect it to be. And so one thing that one could do is to take a second to go back and look at the structural data after preprocessing for those subjects specifically, and actually, and this again looks as though something is gone wrong, and it's very different from how other subjects look like. And again, subject 90 presents these weird patterns of the data. And one thing that I wanted to highlight is how when there's something that is gone wrong, there are various instances or places where that information can pop up and be readily recognizable as something that stands out as compared to the data set. So in this case, if I look at one slide, the same slice for every subject, I can take a very quick, fast, but comprehensive look at the full data set that we're working with. And again, these two stands out for a number of reasons. At the same time, maybe this way of looking at the data is not fully representative of other potential issues that the data has, and perhaps quality control metrics such as QA norm or QA or any other automatic quantitative QC metrics that may be more sensitive to them. So again, it's really sort of like an interplay that is so effective in this case. And if we go back to the quality control for these three subjects, we can see how, for example, while there may be some issues with this particular subject because it seems to be presenting with particularly enlarged ventricles or some sort of like more clear anatomical feature, but like subject 90 again, we can see how the functional data doesn't really show many issues in this case, whereas obviously the structural had a problem. So it is always useful and sort of like necessary to assess both data types for all the steps that the data went through. And so again, depending on the specific case and on the amount of data that is affected by specific issues that we might have discovered by looking at the full data set or individual run level plots or automatic quality control metrics, one could choose to either exclude some data and move on to the next quality control checkpoint, and generally speaking, proceed further, or it may be useful to revisit the prior analytical choices. And so in this case, quality control could be sort of like a tool suggesting different approaches. So for example, if the distribution of the normalized anatomical norm ANAT metric was homogeneous across my data set, but from a visual inspection point of view, although very homogeneous, but they looked like that normalization had performed poorly, one might, for example, decide to sort of take a step back and reprocess the raw data using a different brain template, for example, and then reassess how the data set as a whole is performing. In our case, the two subjects that we looked at, 88 and 90, together with some other ones, were excluded, and we had moved on to evaluating the effect of denoising specifically on the data sets. So a way to look at to assess whether the functional time series, the quality of the functional time series, both from an improvement standpoint, as well as how much residual bias is still present in the data. A good way to assess these two complementary aspects could be to looking at whether the functional connectivity values that can be extracted from the functional time series are systematically biased by some nuisance factors. For example, one of which is motion, for example, or the number of scans that have been regressed out. And this can be done at a run or subject level, so looking at the functional distributions plots, and also can be done by assessing the impact of nuisance factors at the dataset level by looking at the associations between quality control and quality control metrics such as nuisance factors and functional connectivity values. So in our case, if we look at the functional connectivity distributions for just one site out of the 7 that constituted the original data set, one could, if we look at the functional distribution of site number 6, these represent basically the Pearson's R correlation coefficient, which is plotted on the x-axis, between the bold signal time series among all pairs from a fixed 1,000 random voxels, which are extracted from the gray matter. And so here, before denoising, so before regressing out potential nuisance factors, this site presents with somewhat of a typical distribution of functional values. And these are, for example, the fact that residual bias tends to shift the entire functional FC distribution towards stronger and positive values. So there are very few that are negative. It biases the center of the distribution, but also it modifies the shape in a manner that is highly variable across runs, and again skewed towards positive, severely skewed towards positive values. Whereas after denoising, what one let's say a low level of residual noise is represented by distribution. There are center around 0, such as in this case, and there are more similar across participants. So there's less variability in the shape of the distributions. And lastly, they are somewhat more symmetrical with only slightly longer positive than negative tails. So in this case, for example, the tail of this distribution seems to go towards 0 closer to minus 0.4 as compared to the positive tail that is higher around 0.4 and continues up to almost 0.07, 0.06. The other way to look at residual improvement after denoising is to look at quality control functional connectivity, so QCFC associations, and these are generated from the same 1,000 random voxels as the functional distributions were generated from. But here they represent inter-subject correlations between functional values and nuisance factors of choice, and in this case I have selected 3 of them at the dataset level. So in this case, the quality control QCFC after denoising, as expressed, for example, in this case by, actually, let me find another example. In this case, so the the QCFC distribution of our data, as it compares to a potential sort of like an expected distribution that is expected by chance as computed using permutation testing, which is represented by this red dotted line. Our data matches that at a 93% level, which is slightly below sort of like 95% or above threshold that's usually recommended. And matching at a 95% level is sort of like indicative of what could be interpreted interpreted as negligible modulations of these specific nuisance factors on the functional connectivity across the data set. And so what we have done in this case was to identify a few subjects that seems as though they could have been driven this distribution to perform in such a way that the nuisance factors were still having some impact at the data set level. We excluded them and reevaluated the dataset performance with the same nuisance factors, and in this case, we found an improvement, and that was true for invalid scans as well as mean motion and proportion of valid scans as well. Valid scans. And so if some issues are found either from the functional FC distributions or the QC-FC match were not satisfactory, for example, below a 95% threshold, one could decide whether to exclude some data, maybe by changing the threshold for how outlier volumes are identified, and exclude them and sort of like reevaluate having excluded that data as we have done and as I showed you, or alternatively, this quality control checkpoint might be used as sort of like a suggestion for changing analytical approach. And so perhaps again, going back at the beginning and changing preprocessing or denoising strategy might be something that one wants to explore. And so the overarching goal of quality control can be summarized as, trying to achieve four goals in a way. One is to evaluate the data quality improvement on one hand, and also the amount of residual noise that is still in the data. Quality control can be thought of as a tool to identify data to be excluded because it was corrupted and that was not something that analytically it was improved enough or enough with respect to data sets. And QC again could inform some analytical choices and with that respect help drive some of the choices for approaching the data sets. And ultimately, critically, it's useful to know your data, which is important for results interpretation, which obviously is the overall goal of performing analysis throughout. And with that, I want to thank everybody for their attention. And I just want to take a second to say that I was fortunate enough today to give the presentation, but of course, these are the true faces that inspire the most of the work that I presented today. Alfonso Nieto Casagnon and Susan Gabrielli for their support and for making many of these analytical efforts possible by building and maintaining the CONN toolbox. So thank you, everyone.